Sorry, actually, I had to attend to something. Yeah, so what I'm saying is like more or less every country have the procedure, but the performance requirements, I mean performance models and climatic considerations, and at what we say conditions, at what conditions we have to test a particular material, those things will vary. So the important thing I want to mention, another important thing I want to mention is, say for example, we say elastic modulus or resilient modulus as input, asphalt input per pavement design. But that resilient modulus we suggest using ASTM standard, okay, a specific standard number, okay. But you have to follow the same, whatever the procedure that is mentioned in the respective guidelines. Whether if it is an Australian guidelines, you have they suggested how you want to test the resilient modulus. They have specified some loading conditions. Okay. Similarly, in IRC 37, with the it is there has been material property specific testing. How you have to carry the test. You have to exactly follow the same procedure, because that is based on the results from such tests. These models are calibrated. So it is very important to test according to the recommended guidelines and the what we say the conditions at which we have to test. For example, resilient modulus for an asphalt material, it is suggested to use zero point 0.1 seconds loading time and 0.9 seconds rest period. You have to strictly follow such guidelines. Okay. So that is general framework that what we have discussed yesterday. But we discussed uh, what is distress prediction models, okay, uh, and also some of the traffic parameters we such as load distribution factors. What is the why we are having load distribution factors, okay, how to predict the if you forecast the traffic, those aspects we discussed. The one aspect that is left in terms of traffic parameters is the damage factors or equivalent axle load factors. So we said this is, I think this is the last slide where we stop. Okay. So this is the equivalent axle load, total axle loads is basically this is the sigma. So sigma of sum of Fi multiplied by Ni. Fi is equivalent. So the respective damage factor, okay, equivalent axle load factor for the ith axle load group. So we said we have a number of axle load groups, like say 10 kilonewton axle group. Obviously, we will not have 10, but I'm just saying because you want to take commercial vehicles only. So you have 20 kilonewton, 30 kilonewton, okay, 40 kilonewton, 50 kilonewton, and so on. Okay.
Sir,
Obviously, this is yes.
sir, what is the implementation of this equivalent standard axle load in pavement design? Could not get it, please again, sir.
Okay. So equivalent stand axle load factor you are talking about.
Yes, sir.
So if you remember, we were talking about you want to convert all the traffic. So we said yesterday we were discussing about standard vehicle, uh, fixed vehicle approach, isn't it? We said we are following fixed vehicle approach for the design of payment. So I was saying yesterday, you want to convert. We consider 80 kilonewton axle as a standard axle, okay, which means you want to convert all the axles So obviously, so I'm just giving you an example. You have a different types of axes, isn't it? So you have, you know what is axle load. Say for example, you have 50 kilonewton axles. Okay, this is axle load groups. Okay, we have 50 kilonewton axle load group, 60 kilonewton group, 70 kilonewton group, similarly 80, 90. I'm just giving you an example. So say for example, these are all different axes, axle load groups. Assume these are dual axis. Okay. What we are saying is 80 kilonewton axle as a standard axle. That is what the MSA is. I'm talking about 20 MSA, isn't it? My example. MSA is million standard axis. So whatever traffic you are getting, you will be getting on a pavement. You have to convert all the traffic, whether you are having 50 kilonewton, 60 kilonewton, 17 or 90 or 100. We have to convert that into 80 kilonewton. Okay. So that 80 kilonewton we can convert. Say yesterday I was also talking about frequency. Say for example, you are having 100 vehicles per day, say 200 vehicles per day, 100 axes per day. Okay, similarly like this is 50 axes per day. Okay, and this one 80, 100, something like that. So you want to convert everything into 80 kilonewton. We can convert that by multiplying a factor. Okay, so which is, we call it as a damaging factor. Okay, so maybe because the term we used is Fi, let me use Fi. Okay, so what this damaging factor is, what damage, what, relative to 80 kilonewton, how much damage 70 kilonewton axle is causing on a pavement. Okay, that is what the Fi till gives. So relative damage to 80 kilonewton is what the equivalent axle load factor. Okay, say for example, obviously because you want to assume this is causing some damage of some damage. Okay, 100% damage. So the 70 kilonewton obviously cause less damage. Maybe it is causing 200 percentage, sorry, 50 percentage of damage that is caused by 80 kilonewton or 60. So if it is 100% is caused by 80 kilonewton, only 60% is caused by 70. Whereas 100 will cause 200 percentage of damage. I'm just giving you an example. Okay. So that we are converting using damage factors, equivalent axle load factors. But how much damage, that we will discuss. But how do we get these
Sir, from where we are getting this damage factor for each axle load? 30 kilometer.
My next slide will be talking about that one. So now you understood what is damaging factor. Okay. Maybe my next slide will be how we are getting, how we got and how we calculate these damaging factors. Okay. So obviously, see, this is axle load group, but a vehicle, yesterday I have shown you, a vehicle might have it will have one, say for example, okay, say this is, if this is a vehicle, okay, it might have, this is front axle and this is rear axis. Usually rear axis are dual wheel. Okay, so for this vehicle, what you do is you get an usually carry out the axle load survey, and you get what is the load group, in which load group this can go, and you do the perform the axle load survey, and in which load group this one would go, what you put in that way. So obviously this is a separate load group you will have for the single wheel, separate load group for dual wheel. Okay. Say for example, another vehicle has come, which has got another dual wheel axle, tandem axles it has. So what you do is this will you input into different group. Okay.
Hello.
Yes.
Sir, do we see these criteria for the rural roads also? Because in the rural roads, we see only the CBR and the traffic category, T1 to T9. Then from the catalogs, we develop the pavement thickness, base and sub-base. So what is the fun of these rutting depth and other parameters which you are showing, the applicability of these for the rural
See,
roads, like the
no,
PMDS?
no. So IRC SP, you are talking about SP72.
Yeah, SP72, yes, sir.
So in SP72, although they have given only the chart, in the background they have done this work.
Okay, in the background, but sir, but in the field we only calculate CBR value and the traffic category, while the rutting depth and the other modulus of the elasticity, we never calculate.
No, we do not calculate in IRC 37 as well. We just calculate the tensile strains. Okay. But what I'm saying is SP72, when they were developing SP72, they have done this exercise for different CBR values. What is the elastic modulus? When the responses are obtained, when they put into such performance model, what are the thicknesses they are getting? They have given those thicknesses, indicative thicknesses directly. Because to make the job of the designer easy, they have done that thing in the background.
Okay, sir.
Okay.
Okay.
So that approach is followed in many. For example, in UK, still they follow CBR approach. Okay, they do not follow mechanistic empirical approach. But that doesn't mean that they haven't done this exercise. They have done this exercise, and to make the designers work less complex, what they have given is they have given a charts from the CBR. They can select the pavement thicknesses and everything. Okay. So,
So what about the national highway codes? What about the national highway codes? Do we calculate the rutting thickness and the modulus elasticity?
No, for national highways, they have to follow IRC 37, isn't it?
Okay.
So they have to run the IIT pave analysis, layered elastic analysis, and they have to obtain the strain and input in the performance models and get the life of that pavement.
Okay, sir. Okay, sir. Thank you.
Okay. So this is the damage factor. So the sum of all those damage factors together, what we call it as a equivalent standard axle loads. Okay, equivalent standard axle loads. That is what. So Fi is equivalent axle load factor or a damage factor we call. Then the question how we got this damage factor. This is actually in words the same. For the designing a pavement, it is necessary to have information of equivalent axle load factors and expected axle load spectrum. So axle load spectrum is for different axle load groups. Okay, we have seen the axle load spectrum, but I'll show in next example as well. Axle load spectrum. Axle load spectrum is number of passes of axis for different groups of axle loads. Okay, so you have single axles, okay, tandem axle and tridem axle, and each having different load groups. Okay, so we have to separate basically based on these three categories. That is what it is, axle load spectrum is. And equivalent axle load factors, which is indicates the relating damage effect, is a function of the type of pavement, composition and strength of the pavement criteria defining the performance damage. So what exactly is you will get to know this one. So I'll come to this bit later. Maybe this slide you will get to understand if I discuss next two slides. So to determine what damaging effect of each different loads, what they have done in ASHO road test, as I was showing yesterday, what they have done is they have constructed number of roads, okay, both flexible pavement and rigid pavements with a different combination of thicknesses and different combinations of subgrades. Okay, and what they suggested is, okay, a factor called a fourth power law. Okay, fourth power law is nothing but what they suggested: equivalent axle load factor equal to axle load by standard axle load power 4. Say for example, as I was saying, in India we take 80 kilonewton as a standard axle. So in denominator we have. So you want to say, for example, you want to find out what is the damaging effect of 160 kilonewton, okay, dual axle relative to the our standard axle of 80 kilonewton. Okay, if you want to determine the what is the damaging effect caused by 160 kilonewton axle relative to the our standard axle of 80 kilonewton. So what you do is 160 divided by 80 power 4. Okay, so this is 16. Okay, so what it means is if your axle load is doubled, okay, your relative damage is increased by 16 times. Okay, say I'm just giving you an example. Okay, if for a certain time period, if damage is caused by 80 kilonewton standard axle is X, for that particular time period, the damage caused by 160 kilonewton, which is double of that one, is 16x. Okay, so that is what the equivalent axle load factor or damage factor, for simplification we also call as damage factor. So that is what these FIs are. Okay, here whatever FI we are talking about, that is this is how we define. How did they come up this? So they have constructed pavements with the different thicknesses in the sense, like in for now remember it is a same as structural number. So thicker the pavement. Yes.
Hello.
Yes, go on.
Sir, equivalent standard axle load factor equal to vehicle damage factor as 37.
Hello, can you repeat the question?
Sir, there is a vehicle damage factor in IRC 37.
No. Vehicle damage factor is Vehicle damage factor is slightly different from axle load factor. Okay, equivalent axle load factor. So vehicle damage factor is actually, say this is, I'm talking about one axle. Say for example, you have axle, you have a vehicle with say one front and two another axle, the rear axle. Okay, so vehicle damage factor is what is the, say this is this axle is something maybe assume both of them are durable just for now. Okay, this is having say 160 kilonewton axle and this is also having 160 kilonewton. Then vehicle, the damaging effect that is caused by this vehicle is sum of these two. Okay, so vehicle damage factor is slightly different from, the concept is the same, but the here we are talking about only single axle. What is the effect of relative effect in terms of single axle? But the relative effect of vehicle is because it has got two axles. You have to sum up the effect of this axle and this axle, both the axes. Okay, that is vehicle damage factor. Hope that is clear. So in ASHO rotation, what they have done is they have constructed the pavement with different thicknesses. Assume the structural number is actually slightly different, but assume that for now structural number is same as the thicknesses. Okay, so different thicknesses they have constructed, and what they have done is they collected the performance data. So what they have done is accelerated pavement testing they have done. So they forcefully run heavy loads on the these test sections, and what they have found is this is 18 kips. 18 kips is equivalent to 80 kilonewton. Okay, this is in pounds per square inch. Okay, so because in US they talk in terms of pounds and inches and foot. So which is 18 kilopascal is close to 80 kilonewton. Okay, 18 kips is equal to 80 kilonewton. You can see for that the equivalent load factor will be 1, same as whatever we use. But for 2 kilonewton it is 0.02. Say 8 for 18 kips is causing 1 x damage. Okay, whereas this relative to 18, how much 2 kilo kips axle is causing is 0.002x, whereas 40 is causing like nearly 40 times of x. Okay, so based on these analysis, what say if you run the if you put these values, for example, I'm just giving you say here I'm taking this one 12, so 12 divided by our standard axle 18, say power m equal to 0.16. Okay, so if you find out m from this, your approximately your m will be 4. Okay, so this is how the actually that fourth power law has come. Not exactly, but close to 4 should be. So IRC 37 and also in ASHO equivalent load factors, for converting a single axle with single wheel, you can use the equivalent standard axle load factor. Weight of the single axle divided by 65 power 4. Okay. Similarly, for equivalent axle load factor, for converting, say for you to convert into single axle with the dual wheel, if you are having single axle dual wheel, this is what you use. Okay, if you are having tandem axle with the dual wheel, this is the expression: weight of the tandem axle respective axle group divided by 148 divided by 224, and again all of them are fourth power law. This is how you convert axle load factors into, I mean, you will determine equivalent axle load factors. So as I said, we'll talk about this one later. So equivalent axle load factors are usually obtained from the field observations of performance of pavements carrying different types of axle loads. That is what the ASHO road test that I was talking about. Okay, the ASHO road test, they have obtained the that fourth power law based on the ASHO road test. Equivalent axle load factors can also be obtained from theoretical exercise using appropriate mechanistic criteria. Okay. So equivalent axle load different from, so for example, maybe I'll discuss this one later as well. Say if you plot a tensile strain versus number of cycles to failure, and if you plot, if you carry out the laboratory test, you get the slope. Okay, inverse of the slope will be usually a factor of 4. That is what from you can theoretically exercise as well. Okay, equivalent axle load factors are different for different types of pavements and for different performance criteria. So this factor is 4 for asphalt pavements. For example, for concrete pavements, it is usually between so 8 to 12. Okay, so what does that mean? So for asphalt pavements, if you double the load, the relative damage will be 16 times. Okay, but whereas for concrete pavement, if you double the load, say if I take an intermediate value of 10, okay, axle load divided by standard axle load power 10. So what does it mean? If I double, it will be how many times it will increase? 2 power 10 times. Okay, here it is 2 power 4 times. The damaging effect will be increased. Okay, whereas for the concrete pavement, it is 10 times. So relative damage in concrete pavement is much more than for heavier loads. That's why like very heavy loads, the damaging effect for the concrete will be very high. Okay. So this is what is the what we say damaging factor or equivalent axial load factors. So how do we incorporate this into pavement design? So we can incorporate this into pavement design only if we carry axial load measurements. Okay, if we so what you have to do is you have to carry out axial load survey. So to estimate the total projected reputations of commercial traffic in terms of reputations of a standard loads, which is if you want to determine what is the total number of standard axes in millions. Okay, usually your traffic will be in million standard axes. Okay, what you have to do is axial load spectrum is obtained by conducting axial load survey, okay, of commercial vehicles. So obviously you cannot test each and every, you cannot carry out axial load survey on each and every commercial vehicle. Axial load survey is nothing but basically what you do is you have a portable weighing pads and you randomly stop vehicles, commercial vehicles, and measure the front axle weight and rear axle weight. Say for example, if it is having 3 axes, one front axle, 2 rear axes, then you take the axle load weight of each axis and you note down what is the say for example, maybe I'll explain this one. So what you do is, say for example, you have first vehicle you stop and which was found to be a dual axle trailer. Okay, then you have front axle one, maybe rear one, rear two. So vehicle one, what you do is some category of truck. So what is the front axle? What you do is you will determine the what is the load. Say for example, this one has got front axle has got 6 ton, rear axle has got say 8 ton, and second rear axle has got say 8 ton maybe. Similarly, maybe you stopped another vehicle. This has got only one rear axle and one front axle. Okay, and you may have to tell which one, whether it is a tridem or tandem. Okay, so I'm just giving an as a tandem. You do not have any tridem. I'm just as an example. So this one has got 4 ton, 7 ton. Similarly, you carry out for number of food trucks and you will classify. Okay, how many, what we say, how many are within less than 5, how many of them are between 10 to 20, how many of them are 20 to 30. Okay, that is what the axle load survey is about. Maybe I'll, so based on that, what you do is you classify like this. So I'm just giving you an example. So what you have to do is you have to select a adequate sample size. So what sample size is given in IRC 37? Okay, so around 20% of commercial vehicles you have to perform. Okay, but depending on the commercial vehicles per day, that criteria will change. That criteria is in IRC 37. We'll also discuss later. Okay, but I'm talking about general principles. Usually, wheel loads are measured. Okay, because obviously on a portable weighing pad, you cannot put an entire axle. Okay, only wheel load, but you take axle load as 2 multiplied by the wheel load. Complete axle load can be obtained using two-way pad. So if you want to determine the entire axle load, you can use two-way pad as well. Obviously, commercial vehicles in both directions. This is very important, both directions. The reason is, say for example, one way it is going to some industrial area, and the LHS is for the industrial area and RHS is coming from the industrial area. Then if you take only one direction, in one direction there might be loaded say maybe quarries. Say if for example, this is assume this is a divided carriageway. So you have a quarry in this direction, and the vehicles go in one direction, and maybe they come in other direction. So for example, if you collect data for only this one, what will happen? You get much less weights, axle load weights than the vehicles that are coming from the quarry, because quarry they are coming with the stone. So it is very important to conduct survey in both LHS and RHS. So if you take only LHS in this case, you will have less damaging factors, less axle loads than what it is supposed to be if you are taking excessively high. So only if you look into both of them, you will get some understanding. Okay, so I'm just giving you an example. Okay, consider one of us has done the axle load survey, in which 1,000 commercial vehicles were stopped and each axle was measured. Okay, so you have stopped 1,000 vehicles, and total axles you have got is for all those 1,000 vehicles 3,400, because every vehicle will definitely have two axes, but some have 3 axes, some have 4 axles as well. Okay, some might have 5 axes as well. So in total you are getting 3,400 axes. Okay, the total number of single front axis is 1,000, obviously because you are conducting 1,000 commercial vehicles, your total number of single front axis will be 1,000. Number of rear single axles with dual wheel is 1,100. Number of rear tandem axis is, you know, we discussed what is tandem axle and tridem axis. Okay, so you have 1,300 tandem axis, and assume you do not have any tridem axis. So the distribution of axle weights for each category is given in the next slides. So this is the distribution. For example, what you did is you have done the axle load survey and you found 3,400 axes, and you categorized them into single front axis, single axle with dual wheel, tandem axle with dual wheel. Okay, 3 categories. Okay, this is what. So distribution of weight, and you categorized into different load groups. So this is a single axle with single wheel. You have 0 to 20 one load group, 20 to 41 group load group, 40 to 60, 60 to 80 another group. Similarly, the distribution for single axles with the dual wheel is 20 to 60, 60 to 100, 100 to 140, 140 to 180. Similarly, tandem axle with dual wheel 40 to 100, 100 to 160, you categorized. But remember, this is an example, but actually according to IRC 30, you have to do in intervals of 10 kilonewton for single axle single wheel, 20 kilonewton for single axle dual wheel, 30 kilonewton for tridem, tandem. This is single axle 10 kilonewton, tandem axle 20, tridem axle 30. But just for example explaining you, this example is given. Okay, and when you categorize, you got 100 vehicles. Obviously, these all together should come 1,000. Okay, 100 vehicles which fall in between load group of 0 to 20. 250 fall in 20 to 40, 400 fall in 40 to 60. So we just for simplicity, what we are doing is we are taking midpoint. Okay, this is 10. The midpoint of 20 to 40 is 30. 40 to 50 is 40 to 60 is 50 and 70. Okay. Then now you want to calculate damaging factor or equivalent axial load factor. Equivalent axial load factor is for this one. I'm talking about this one. How much? 10 divided by what value should I use? So I have given 65 here. Okay, we have to use 65 for if you remember, for single axle with single wheel, weight on a single axle divided by 65 whole power 4, isn't it? So that is what we are doing here. So 10 divided by 65 whole power 4. If you run the calculation, you will get 0.056. You can parallelly work on whether these values are correct or not. You can check. Okay. If you do this one, you will get 0.0056, and if you multiply this with 100, you get 0.056. Okay. Similarly, if you divide 30 divided by 65 whole power 4, you get 0.045. If you multiply with this with 250, you will get 11.344. Similarly, for this load group, this load group. So what does this mean? Entire exercise means, so you have 1000 single axis with single wheel loads is equal to how many standard axis? 0.056 plus 11.34 plus 140 plus 336. Okay, which should come around 487.71. What does this mean is, although you had 1000 single axis with single wheel loads with varying load distribution, that is equivalent to only 481 standard axis. Okay. Similarly, if you run the same exercise with the distribution of single axle with the dual wheel. For single axle dual wheel, what is the standard axle? 80. So if you divide 40 with 80 whole power 4, then you would get 0.065. Okay, maybe it will be good exercise for you if you do by yourself this thing. So 40 by 80, you will get 0.025, and if you multiply with that with 100, 625. If you run the same, obviously because it is 80, you will get 1. If it is 120, 5.062, 16. So these are axial load factors, and you multiply with this one. So what does this mean? So you have how many in total? 3, 5, 1100. You have 1100 vehicles as well. 1100 single axle with the dual wheel are equivalent to 6000. Only you have 1100, but that is equivalent to 6037.5 standard axis, which is standard axle is 80 kilonewton single axle with dual wheels. Okay. Similarly, if you run the analysis, run the calculations for tandem axle with the dual wheel. For tandem axle with the dual wheel, I think it is 124 is the factor. Let me see, or 148 maybe. 148.
Sir, I am Om Prakash Sinha from RCD Bihar, assistant.
Mhm.
Instead of considering different load groups, if you consider mean of that load groups, then what is the effect on the equivalent axis load factor?
No, say that again. You want to calculate mean of which load groups?
I'm considering here the different load groups, 20 to 40 and
Okay,
100 to
this one
160.
for
If you consider mean of that group, load groups, suppose for 40 to 20, I'm considering mean of that, average
that is
of
what
that.
we are doing, isn't it? So 40 to 100, I'm taking the midpoint, which is 70, which is mean.
Now, instead of taking 70, if you consider 40 to 220 mean. Suppose,
40 to 220 mean.
yeah.
So
Then what?
What will be the effect? That depends on your frequencies. Say for example, if you have more vehicles here, and here in this case there are more vehicles here and less vehicles here, for example, I'm just saying, then your total, what we call it as a damaging factor, will shift to the right. If it is you have more vehicles here, it is more than. So basically that will depending on how many vehicles you have in upper group, how many vehicles you have in lower group. Say for example, obviously your standard axle is somewhere 80. If you have more vehicles on the top and less vehicles on the bottom, your damaging factor will be overestimated.
Okay, sir.
Okay. Or if it is other way around, it is underestimated.
It means that it affects the cost of the design.
No, that depends on your distribution, load distribution.
Okay, sir. Thank you.
Okay. If you have heavier vehicles, more heavier vehicles and less lighter vehicles. Okay.
So do we keep the factor of safety for these? I mean, like in the RC design, we keep factor of safety. For the road design, do we keep the factor of safety?
So we do not have a factor of safety, but we have reliability factors. Okay, which I'll be discussing later when I'm discussing the performance equations. We do not have directly factor of safeties, but we have reliability factors in performance, which I'll show you. Okay.
Okay, sir.
So what it means is, if you run 1300 of standard axis out of 3400 is equal to 3096 standard axis. So that is how we calculate the damaging factor. This is an example, but in pavement design, if you are running the design, it might be a bit more complex, because you will have different vehicles. For each vehicles, you have to either categorize into, either you determine vehicle damage factor or axle load factor. Okay. Basically, what people do is, instead of finding out axle load factor, they categorize each pavement into different vehicles. I mean, each axle load survey into vehicle groups, and for each vehicle they determine the vehicle damage factor. That I'll show you either today or later today or tomorrow. I'll show you those calculations as well, but the concept is the same. So what it means is, although you have 3400 axes, what you have counted, the total standard axes are equivalent to 9621. Okay, so 1000 commercial vehicles, whatever you have surveyed, is equal to 621.8 standard axes. Obviously, when you are carrying out axle load survey, you consider only 10 or 20% of the axle, and you have to factor that to 100% per year. And if you consider with the growth factor for design life, this will be in million standard axis. Okay, here only you have 9000, but if you are carrying out for a national highway for 10, if you forecast everything to the your design life, it will be definitely in a million standard axis. Okay, but the concept I'm explaining. And vehicle damage factor is something, is this one. This is for whole group, but we also do individual vehicle factor damage factor as well. Vehicle damage factor is 9621 standard axis divided by 1000, because you have carried out 1000 commercial vehicles. So on average, each vehicle is causing, if standard axle causes X damage, okay, each vehicle on average is causing 9.62 times of X damage the vehicle is causing. That is what vehicle damage factor is. Hope this is clear. I have one more slide. I think. Use it for converting a given traffic volume into equivalent number of standard axes. VDF is typical value representing the loads carried out by the commercial vehicles plying on the velocity. Rather than axis, if we find out the damaging effect caused by each vehicle, we call it as a vehicle damage factor. Okay, determined by conducting obviously axle load survey. So this is about what are the traffic considerations. In summary, what we have discussed is how we forecast the traffic. Okay, for forecasting, how we forecast. For forecasting, we need growth rate. Okay, and how we account for lateral wander and lane distribution. Okay, lane distribution we discussed. We have lane distribution factors, and then we also discussed about axle load factors or damage factors. So based on all these three, what we find is design traffic. So I hope you understood what is design traffic. Design traffic always has to be standard axis, in terms of standard axis. Okay. So if you remember, when we are discussing our first lecture, we said three main factors. One is traffic. Okay, so for traffic, what we are interested in to find is design traffic. And material factors and environmental. And obviously performance criteria as well we discussed. So traffic we discussed, material is Young's modulus and all aspects, and environmental factors we discussed in in this one what we discuss is material factors, how they influence, and also analysis. Okay, what is analysis? So basically what we'll discuss is an introduction to the how we determine the stresses and strains. And performance criteria, what is the we already discussed what is the foundation required for the performance criteria, but I briefly show you what is different performance criteria used by different agencies. Particularly I will be showing ASTO empirical design criteria and IRC 37 mechanistic empirical design criteria. Okay, most of the things that I'll discuss in this one is I already discussed, but what I'll be showing to you is what exactly. So I discussed, okay, various materials will be there and how they influence, but what materials will be there in IRC 37 in general, and also I also discussed about how we obtain the performance criteria. But I'll show you actual examples, real examples of those performance criteria in next 15-20 minutes. Okay. After this one, we can take a break. So pavement consists of different types of materials. Obviously, soils, granular materials. We have stabilized soils. Okay, cement treated bases and granular bases, bituminous layers, surface course, binder course, and base, and different types of mixes we have. Say for example, if it is a concrete pavement, you have a concrete as well. Okay. Say for example, you have cement treated base, cement treated sub base. Okay. Similarly, you have BC, bituminous concrete, dense bituminous macadam for asphalt materials, and you have stone matrix asphalt and gap graded rubberized mix asphalt. Okay, so typically we have another semi-dense bituminous macadam, bituminous spectrum, others as well, but primarily these are the mix types we use in asphalt. Okay, so they all fail, not all, but at least bond materials fail by fracture, fatigue, and all materials, I mean not cement treated. So this one, they asphalt and concrete, they fail in fracture. Okay. Whereas permanent deformation, asphalt and unbound materials, they fail in permanent deformation. All layers fail due to durability issues, obviously. Okay. So this also we discussed. The material is subjected to various conditions. It will be subject to different stresses, different load durations. Stresses is, say, for example, if you are having heavy vehicle, the stress will be more. If it is lighter vehicle, stress will be less. Duration we discussed. The faster vehicle will have a less load duration. Slower vehicle will have longer load duration and different rest period. Okay, a trailer is immediately followed by another trailer. You have less loading time. Say, for example, within each truck, if front wheel will obviously pass immediately after is followed immediately by the rear axle, then the rest period is less. But if a truck followed by another truck after a long time, like the rest periods will be more. So it is subjected to different rest period. And aging means obviously asphalt materials age with time. Okay, oxidize with time, so which becomes the bitumen present in the asphalt become brittle, and it is subjected to different moisture conditions. Immediately after monsoon or during monsoon, the moisture will be more. If it is during summer, moisture will be less. Okay, what it means is it is all the materials are subjected to different environmental conditions. Similarly, temperature during daytime, higher temperature, during nights, lower temperatures. Okay, so in essence, obviously all materials will not be influenced to the same magnitude for all these different conditions. For example, what we say, only asphalt is influenced by load duration. Okay, similarly rest period is influences the both asphalt and unbound material behavior. Okay, moisture, all actually, but primarily unbound materials. Stiffness of unbound materials is influenced by moisture, but it will have less influence on the stiffness of asphalt or concrete. Similarly, temperature is significantly influenced by asphalt. Okay, so this you have to understand when you are designing a pavement. Okay, but obviously the guidelines are such that we do not have to think about most of these, but as a designer, if you want to make changes somewhere, you want to think about all these aspects. So time, temperature, moisture, stress and age dependent properties, that is what we have to determine if you want to input the material input into the pavement design. Say for example, resilient modulus of an asphalt. Okay, time is specified, loading time. The loading time of 0.1 seconds is specified in ASTM standard, that is recommended by. And also at what temperature of 35 degrees is specified by IRC. Okay, so for example, if you are finding out the CBR, okay, moisture, at what moisture content you have to determine is specified. Okay, for example, resilient modulus of an asphalt layer, what stress level you have to test the sample, that is specified. Okay, all these are specified in the usually in the standard, because carrying out the test at so coming to the material behavior, different materials behave differently. So they are usually termed in terms of stress strain relationship, usually characterized in terms of stress strain relationship, ability of the material to recover after release of the load, and time dependency and temperature dependency. What exactly this means is, what is stress strain relationship? How do we characterize this one? By modulus, isn't it? Say for example, if you are talking about Young's modulus, E, what is Young's modulus? stress by strain, isn't it? So that is what the stress strain relationship. For example, if it is there is a linear relation, when if you apply a load, there is a linear relation between stress and strain. We call it as a material behaves linearly to stress. I mean, material responds linear to either stress or strain. Okay, if it is if you are applying constant stress or constant strain, depending on. Okay, so this is linear material, and these are, if it is behavior is non-linear, maybe like this. This is non-linear. Okay, this is what we call stress softening, which is non-linear either way. This is also non-linear. Okay, so in simple terms, say for example, if you are maybe this is in stress strain, maybe if I plot you applied a constant stress, with the time, say for example, your modulus is not changing, it remain constant, say for example, then it is linear. But if your modulus is changing, either it is increasing or decreasing, this is non-linear. Okay, one is the stress hardening, another is stress. Oh, sorry, I think this is stress. Okay, with stress, with increase, I plotted wrong actually. So with increase in the stress, if your stress is increasing and if your modulus is remaining constant, that is linear. But if your modulus is increasing or decreasing with the stress, so I should have then it is non-linear. Okay. What I plotted is viscous and non-viscous. So another property that dictates is asphalt layer, particularly if you deform a load and you release the load, then it will deform and reaches to the complete recovery. Then we call it as elastic. Okay, maybe if it is time depending, if the response is instantaneous, elastic, but if it is not instantaneous, like this, if it, maybe I will draw something like this. So you applied load, obviously this is time. You applied instantaneous load and you release it somewhere here. Okay, if it is completely recovering from something like this, it is completely recovering. This is one case, case 1, this is case 2, and there will be case 3 as well, say non-recovering. Okay, so this is elastic, this is viscoelastic, this is because there is some irrecoverable viscoelastic plastic, because it is not instantaneous, recovery is not instantaneous. Okay, asphalt behave this way. Okay, and also granular materials also have some permanent deformation, although they behave elastically, they will have some deformation. So essentially what I'm saying is they have different types of behaviors. Say for example, so you understood what is elastic, linear and non-linear, which is with increase in the stress or decrease in the stress, the modulus should remain same. Say for example, unbound materials, they are linear, non-linear, elastic. Okay. Asphalt is maybe within the, we can assume it as a linear viscoelastic. Similar, concrete, linear elastic. What other materials we have? So you can see this is non-linear elastic, granular materials. Asphalt is linear but viscoelastic. Concrete, linear elastic. So each material within the pavement behaves differently. Okay. Actually, asphalt is linear viscoelastic plastic. Maybe I should talk about plastic as well. But when we are analyzing a pavement, what we do is we consider all materials as elastic, irrespective of although asphalt is viscoelastic plastic and unbound materials is non-linear elastic plastic, but we ignore all of them and consider as an elastic materials. Okay. I'll come to this slide.
Yeah, a question.
Late. Yes.
I'm having a question. Why it's considered elastic only? All.
So because considering all these material theories into a pavement design, it will be very complex, very complex, because elastic theory has developed, but you have to develop viscoelastic theory, non-linear viscoelastic theory, and analysis is difficult. The entire process is very difficult. But what people have found is, say for example, if you want to run a non-linear elastic, okay, maybe you may have to run the finite element models. Okay, the softwares maybe we have to develop much more complex software for the analysis. Okay, if you are doing some research, you can consider non-linearity or viscoelasticity. But in theory, we assume all the layers are elastic, and also, as I indicate in the next slides, you can see here, though bituminous materials are viscoelastic, actually we should also say viscoelastic plastic. Plastic means there will be some permanent deformation for every load application. Okay, and granular layers and substrates are non-linear elastic. Only linear elastic layered theory is commonly used. Okay, linear elastic theory is only. We do not use viscoelastic plastic or non-linear elastic theories. Okay, because one particular reason is the load duration is small under fast moving loads. Because if the load duration is small, usually the materials, whether if it is a viscoelastic material or a non-linear elastic, the behavior after number of repetitions, it will be elastic. Okay, that is different theory. Maybe we might not have time for explaining all those, but in general, for a small durations after number of repetitions, whether it is viscoelastic material or non-linear elastic material, they all eventually behave as an elastic materials. Okay, so and also what people found is analytical results usually matched with the measured values when appropriate material inputs were selected. So what people have done is they have run the elastic layer theory and found out the responses, stress and strains, and also they measured from the field measurements, and what they noted is the field measurements and the output from the elastic layered analysis, if appropriate material inputs are selected, they match. That's why people are compromising to make the design process easy. Okay, but as a researchers, people still use viscoelastic theories, non-linear elastic theories for unbound materials. Okay, in fact, some, say for example, if you have heard about a program called KenLayer, it runs the analysis based on viscoelastic models. Okay. But for simplicity, we only consider the elastic layer theory.
I have a question.
Yes, please.
Is there any criteria for selecting factor of safety for granular materials?
What do you mean by factor of safety?
For materials which are using in construction.
No. As I was saying, so factor of safety, I mean, for what property you are talking? Say, for example, if you are considering about, see, we have explicitly have factor of safety is number of locations. Say, for example, you are taking the CBR value. Okay, say you have a 10 kilometer stretch. Okay, you have at maybe every 100 meters or every 200 meters, you do the trial pit. Okay, and bring the soil to the laboratory and you test for the CBR. Okay, maybe you have collected say 100 or 50 trial pits and you have conducted 50 CBRs. And obviously you will not get same CBR for your entire stretch, isn't it? What you are doing, you are taking 85 percentile value. That means we are being conservative.
I'm talking about the material those were taking from the direct from the queries, from the using GSB and WMM.
No. With those as well, it's the same, isn't it? You carry out the CBR test. Okay. CBR test, you will not take the CBR that is maximum you are getting. So there is not explicitly, we are not introducing any factor of safety, but within the design process as well, there are many ways which we are being conservative. Okay, for example, material models, or for example, what can we say? You are talking about the granular materials. Granular materials, are you talking about CBR value or grading envelope? So grading envelope, we are giving the upper bound and lower bound. Okay, so not explicit, like specifically we are giving, but there are some factor of safety inbuilt. But depend you unbound material, in what way you are talking about factor of safety? Can you tell me?
I'm just checking out the strength of material because the elasticity.
Strength, which strength?
Suppose granular material depends on the angle of friction.
Angle of friction, yes. So if your angle of friction is less, then your CBR, there is requirements for CBR, isn't it? Your granular base and granular subbase has to achieve some CBR. If your angle of internal friction is less, you will not achieve those CBR values.
Okay, I'm talking. Okay, sir. Thank you.
Okay. So although I'm not explaining the elastic layer theory, but in principle, what it does is what in elastic layer theory, we linear elastic layer theory. Again, everything is important in this one. So linear, because it is not linear, very important. Okay, we are assuming the material as a linear material, and we are assuming it as an elastic, not viscoelastic. Okay, we are not assuming it as a continuous mass, we are considering it is a layered. Okay, all these are important. So you can see different layers. We model the pavement into different layers. Okay, whose inputs are elastic modulus and Poisson ratio. Okay, so what we do is we model this into the software, number of layers, whether it is a 3 layers or 4 layers or 5 layers. So if you here you are having n layers. Okay, number of softwares are available. Example like eLayer, IATP, Bizarre, and KinLayer. Okay, all of them they assume under circular contact area. You can see we convert the wheel load into circular contact area and we run the analysis. Okay, linear elastic layers require thicknesses and material properties. Okay, you need H1, H2, H3 values and E1 and mu1s for all these. Okay, this is infinity, so we do not need to input this one. So when you run the analysis, the output will be stress, strain, and deflections at the different points. Usually, what we do is we need 1 point here, 1 point here for a single wheel load, but we'll select at different points. At whatever points you want, you can select those points. You can ask the software to give the stress and strain values at different locations. But what are those locations? I will discuss a bit later. Okay. So maybe we can break for 10 minutes. Okay, in my computer it is 11:17. Let us meet at 11:30. From now I'll be a bit faster because these are all things I have discussed already. Okay, maybe I should be finishing in 10 minutes this thing. After this I will directly go into IRC 37. Okay, still we have discussed many aspects in IRC 37, but exclusively IRC 37, what is written in IRC 37, I'll discuss after performance criteria. Okay, but others can leave, they can come at 11:30. But if you have questions, I can take questions in the meanwhile during the break as well.
One question, sir.
Yes, please.
Sir, in our IRC 37, one mathematical formula for calculation of million standard axle load, that is n equal to 365a, that mathematical formula. So there we are finding the cumulative standard axle load, and in the latter case we have studied equivalent standard axle load, where we are finding the equivalent standard axle load by multiplying a factor of damaging factor. So between them, and which is more suitable for the design purpose?
No, it is the same. See, maybe you might be talking about. Let me open.
When we are putting normally numerical values, we are getting the million standard axle load in one calculation.
Are you talking about this one?
Yes, sir.
So see, F is vehicle damage factor. This is what we discussed, isn't it?
Sir.
This is what we discussed. F is vehicle damage factor. This is 365. R is growth rate. A is initial traffic. D is distribution, lane distribution factor, and F as well, vehicle damage factor, which we discussed earlier.
Sir.
Okay.
Okay.
Okay. So, any other questions?
So, sir, F value, that is vehicle damage factor, all this calculation should be done.
Yes. So basically in actual payment design, although I explained the concept, but what people do is, say we have different vehicle groups, isn't it? Low LCVs, okay, 2-axle trailers, 3-axle trailers. And what we do is we do perform the axle load survey and we determine the vehicle damage factor for each of these axle load, each of these vehicle group. Say maybe LCVs may have vehicle damage factor of 3. This one might have 6. This one might have 8 because this has got more. So we perform this calculation for each vehicle category. For LCVs, we perform this one. For 2-axis, we perform this again calculate, and 3-axis we calculate, and we sum up all of them.
But sir, in some cases, some books, the vehicle damage factor directly given, that is providing, I think, some.
So in IRC 37 as well, it specifies that if the project is small project, you can there are some default values are given for particular. You can, in that case, what you can do is you can do this calculation, okay, and multiply. Here your A will be in terms of commercial vehicles, and you multiply with the damaging factor. For say if your project is not a small project, in that case you can use direct values. For example, I think I might not have put that in here, but there are indicative VDF values that are given in IRC 37. Okay, then you do not have to do individual vehicle classification VDF. Okay.
Okay, thank
you. Okay. Any other?
I have a question. For equivalent load factor, you have considered the traffic in both the directions. Is it depends on the median width? Because median width, suppose it is more than 5 meters, then should we consider the traffic in both the directions, or for considering the equivalent load factor?
No. So in all cases, you should look the traffic in both directions. Okay. The reason is, as I said, if you do not consider one direction, there will be all heavy vehicles taking some goods and unloading somewhere.
Sir, I just want to say in this, I think the two separate pavement design can be done, right? On left side different, right side different. Hello.
Hello, can you repeat
I
that
would
one?
like to
Because
say
I
that
think two
if
people
there
are.
is a median width more than.
Hello.
This regarding the median width, he said. Hello. If the median width is more than 5 meter, means a separate pavement design can be done for both lane, right? Left will be a separate
yes,
pavement
yes,
design,
yes,
right
yes.
will be separate
Yes,
pavement.
yes, yes. Oh, you're talking about in a divided carriageway.
Yeah,
Yeah, if you have
I
a
think he's
divided
talking about divided carriageway, right?
okay, if it is a divided carriageway, obviously you can have different designs for different ones. But what I'm saying is you cannot do uh, vehicle load survey for LHS and design for RHS. Okay, and you cannot do the local axial load survey for RHS and design for LHS. Okay, you cannot use the same vehicle damage factors. Okay.
Sir, you have considered a give an example of query. For LHS, suppose for the vehicles which are carrying out from the query is having loaded vehicle. For the going into the carriage, they are lighter vehicle. Then suppose for that we have considered the different equivalent load factor, or we can consider with the
So if your
load
payment
factor
designs
the
are
highest.
obviously if it is a divided carriageway, if you have a median, okay, if it is a divided carriageway,
Okay.
you can have different designs, isn't it?
Okay, sir.
But obviously you have to
Okay,
provide
thank
the drainage path from one way to another way. Those things are practical things that you have to consider. Okay.
Okay, sir. Thank you, sir.
Any other?
Hello.
Oh, yes.
Sir, we were talking about the factor of safety. Sir, when we take the soaked CBR for 4 days, then
That is being
that is for
conservative.
that is
Yes.
for the worst condition.
Yes.
Yeah, that is
Yes.
for the conservative. And in IRC 37, they take effective CBR. So yeah.
No.
So
Both are different. Okay, effective CBR and soaker CBR.
yeah.
That no. So do not confuse with the effective CBR. Effective CBR, I will explain anyway what is effective CBR. Effective CBR
Yeah.
is when you have two layers. Okay, that is different. Effective CBR is different, and soaked CBR is CBR of the soil material. But effective CBR is a different concept. I'll explain those effective CBR concept later. Okay.
Okay, sir.
Sir,
Yes.
sir, if I still now we have studied only if we form a new road, sir, how we can calculate the vehicle damage factor? No traffic is there. Form a new road.
So
Then
basically, what if it is a new road? The thing is, you have to find a section which is similar to the new road. Okay, obviously you will not have axial loads data and all those things, but you have to find a similar section. Okay.
okay, sir.
And perform the axial load survey.
Okay, sir. Thank you.
Okay. Okay, I'll be back in 5 minutes. By 11:30, I'll be back. हिसाब से मिला है कि टोटल वेतन Okay, hope most of you are back. So far, I think we discussed about material inputs as well. Okay, and how the analysis, payment analysis work, what is the output, why we are choosing linear elastic model, linear stochastic theory for analysis, that we have discussed. Now, maybe this point I have discussed. The linear elastic layered analysis, each layer has to be assigned elastic modulus Poisson ratio values. The first and minus one have finite thickness, the H1, H2 values. Obviously, the last one will have infinite depth. Okay, one of the assumptions for linear elastic theory is the layer in horizontal directions are infinite in direction. Okay, although this is not entirely true, but that is one of the assumptions. And we assume circular contact area with uniformly distributed contact stress. This we discussed yesterday as well. Okay, coming to the what performance criteria, we discussed a lot about performance criteria yesterday, so I will not spend a lot of time on performance criteria. I'll just give, I'll read all these things, but anywhere it is important, I will stop and highlight, because I already discussed these yesterday when discussing different aspects. So performance criteria are nothing but they are models or equations or computer programs or charts, etc. So these all can be represented in different ways, different guidelines, different countries. There some countries adopt in terms of models, some adopt in terms of equations. Some of them have inbuilt computer program. They might have inbuilt in the computer program. Some represent in terms of charts. For example, one of the chart I have shown you, IRC 37 1984 design method. They have incorporated the performance criterion charts. Okay, for example, in IRC 37 we used equations. Okay, some softwares, for example, Ostros, they incorporate this in some MEPDG, they have incorporated this into computer program as well. So there can be number of standard loads that can be served by payment before certain acceptable level of distance. So for example, in our IRC 37, we said n as a function of mechanistic parameters such as strain or stress, okay, or MR, etc., 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 isn't it? So that is what it can be, this in this form, okay, which is the number of standard axis. And if we said number of standard loads that can be served by the payment before certain unacceptable level of distress. This unacceptable level of distress, we said wetting 20 mm for India, cracking 20%. Okay, or in some performance models, they may have some performance criteria after certain number of load applications or number of years. Okay, so those performance criteria, what they give is they have a similar function, but instead of 20 mm, what they have a function of strains or stresses or MR, but the function output dependent variable will be what is the ref depth after 10 years or a ref depth after 50 years. Such models will also be there, some models. Okay, I'll give you examples of each later. So this one, performance is function of payment, traffic condition, climatic condition, which we discussed earlier as well. As we said, the performance criteria is the most important part of the payment, any payment design approach. We discussed this as well. Different agencies adopt different approaches. Okay, usually developed basis on the observed performance of data. The observed performance is correlated to one or more design parameters. Okay, in our case, design parameters such as tensile strain at the bottom of the bond layer, okay, compressive strain at the top of subgrade. Those are the parameters. The relation between the performance of pavement design and the parameters is referred to as the performance criteria. Okay, the performance criteria also I have shown. So usually these performance models have, as I said, different performance models. It can be y1, y2, y3 as a function of some parameters, design parameters. What could be those parameters? We have discussed at least some of them. Okay, there will be some parameters which should use the indication of some distress parameter. For example, we have seen performance model for PSI. Okay, PSI as a function of some distress parameters, isn't it? If it is in that case, we have such models, or in some cases we can have a performance indicator as a function of time. Say for example, say for example, if I have a equation which I have IRA, International Roughness Index, which we discussed yesterday, with time or number of axle loads, then this is we can have such performance models as well. Okay. So that is what has been discussed. So here, if you see, this is an example for performance model or performance criteria that is given in ASTO 1993 model, performance model that is given. Okay, so similar to what we have in NF performance models in IRC 37, this is the performance model that is given in ASTO 1993 model. Okay, this is an example for empirical model. Because why empirical? There is no empirical parameters can be what factors are usually included. So you can see W18 is number of cycles to failure. Okay, I'll just come. Okay, I'll just come in 2 minutes. Okay, sorry for that one. So this is the similar model, like although we said there will be different types of model, similar model to what we have IRC 37, which is number of cycles to failure. Okay, but as I said, this is an empirical model because there is no mechanistic parameter within it. Okay, as you can see, there we have a resilient modulus. Okay, but for us, like we have two different performance criteria or performance model. One is for rutting, one is for cracking. Okay, so we have to design pavement for resistance against both the distresses. Okay, here the performance criteria is in terms of PSI. Okay, which is pavement serviceability index. And I'll explain what are the terms. These two are basically the reliability terms. So this is a kind of structural number, which is I'll tell you what exactly the structural number, but it is a function of thicknesses. If the thickness of the pavement is more, it is the structural number is more. Okay, this is resilient modulus of subgrade. As you can see, number of cycles to failure is given as a function of subgrade strength, okay, and total thickness, reliability, okay, and performance. Okay, similarly in our model as well, we have a similar approach, but for example fatigue, in terms of thickness we give the mechanistic parameter. Okay, see, this is pavement serviceability index. You can see delta PSI, which means, say, basically, usually the serviceability index range from 5 is in the good condition possible and 1 is the worst condition possible. Okay, not worst condition possible, but that cannot go below 1. So the delta, if you have to give the failure criteria. For us, the failure criteria is 20% of crack or 20 mm run depth. But in this equation, failure criteria is loss of serviceability. Say, for example, initially in a new condition, say pavement serviceability index is 4.5. Okay, and say PSI after failure, we assume, say, for example, we consider a failure of 2. If it is PSI is less than 2, we consider it as a fail. Then the delta PSI is 2.5. Okay, so larger this gap, larger this value. Okay, so if you have here plus indicator, larger this value, larger this one. Say for example, if you are considering a very high level road in which you want to consider as 3 as loss of permeability, terminal permeability value, then this one will be 1.5, and your design life for that particular pavement will be less. Okay, same pavement, by changing the delta PSI, your pavement thickness, design life will come less. Similarly, the reliability as well. If you increase the reliability for the same thickness, your WM18 values will come. So what is W18? Number of cycles to failure. But what is this 18 means? It is same because same as our standard axle. Our standard axle we talk in terms of 80 kilonewton, isn't it? But for them standard axle is 18 kips, which is pounds per square inch in terms of thousands. Okay. So you can see this loss of serviceability is again a function of various factors, which is we call it as a slope variance, red depth, cracking, and patched area. Okay, this I'm just giving you to explain those terminology. PSI, what is PSI? And structural number you can see, which is A1 D1, A2 M2 D2, A3 M3 D3. Okay, D's are thickness of pavement, and A are coefficients depending on the difference. Say what type of material you are giving, and what is the drainage. M1, M2 are drainage coefficients. Okay, so if this material is having good draining properties, the M value will be higher. If it is poor draining properties, the M values will be less. Okay, similarly, if it is stronger materials, A values will be high. If it is weaker material, the A values will be low. We call it as a layer coefficients. Okay, sum of all these will usually give the structural numbers. So if you can see, higher the structure number, the higher the WN, W18 as well. This is the performance model that is given in ASTO 1993 model, which is actually many countries, in many states in US still use this model, and many countries, Middle East countries still use this model for design of the payment. Okay. So coming to our, what is the model that we have in IRC 37 2012, and also there is slight modification in 2018 model as well. So this is, we are talking about these models. Okay, number of cycles to failure in rating is this model. We have say, which is epsilon v. This is for 80% reliability. This is for 90% reliability. Say for example, so as per IRC 37, I'm talking about conventional bituminous payment, but obviously different payments have different criteria, but in general, remember. So for example, this is asphalt. This is unbound, okay, granular base and granular subbase. So whatever strain we are, compressive strain we are getting at the top of the subgrade. This is subgrade. This is what we call it as epsilon v. Okay, epsilon v is initial vertical strain on the top of the subgrade. Vertical strain, say you choose a 120 mm of this one and 250 mm of this one. If you with E1 mu1, E2 mu2, and some E3 mu3, and you know thicknesses, you know material properties, and if you input into the pavement, you get the, and if you want to determine the stress strain and deflection at this point, you get the vertical strain, which is compressive strain at the top of the subgrade. If you input whatever value, if you input into this one, what you get is N. Okay, actually number of cycles to failure. Okay, cumulative standard axle load repetition before the pavement develops 20 mm average step depth. This is what we have been talking about. So if you input this one, you get NR. Similarly, for resistance again, this is resistance against retting. So if you want to see resistance at fatigue, what you have to determine is tensile strain at the bottom of the bound layer. So for example, if you determine the stress strain and deflection at this value, and the tensile strain, whatever tensile strain you are obtaining at the bottom of asphalt pavement, and you input into this one, whatever the number of cycles you are getting for this pavement is basically cumulative standard axle repetition before the pavement develops 20% of, so for this one it is 20% of cracks. Okay, so I'll come to what is reliability bit later, but just giving you design philosophy before I go to. So we have two criteria, isn't it? Fatigue criteria and rating criteria. Okay, you run the analysis, and for tensile strain, vertical strain criteria, rating criteria, say for example, you got life for the pavement. You are designing for 20 MSA traffic. Your design, maybe I'll use fresh base. Okay, say I'm designing a pavement. Okay, I want you to pay a little more attention for this one, because this is again the very important point. Which, if you are very familiar with this one, this is straightforward point. Okay, at this location, you want to find out compressive strain. Okay, at this location, this is asphalt bound layer. This is unbound. Obviously, I'm explaining only these two criteria. We have one criteria for rating, which we have seen, one criteria for fatigue. Okay, here you get NR, NF. Okay, for this payment, you have H1, H2, and E1, mu1, E2, mu2 as material properties, and E3, mu3. You input and run into the software, and you run the analysis. You get tensile. You given these locations. You got the tensile strain and compressive strain. You input the tensile strain into fatigue model, and you input the uh, compressive strain into rating model, and you get NR. Say for example, you are designing a pavement for 20 MSCA. Again, our example. So your NR you found to be say 30 MSCA, but your NF has you found to be 18 MSCA. So then can we select this pavement? Someone want to answer?
No.
No. So it has to satisfy both the criteria. Okay. So what we do is we either increase H1 or H2 or change the material you are using or change the payment type until you satisfy both rating and fatigue criteria. Okay. So now coming to what exactly the reliability is. Reliability levels you choose based on which type of payment you are considering. Say for example, if you are considering national highways or some state highways with heavy traffic, you choose the equation for 90% reliability. Okay. So this is actually reliability is kind of confidence. What confidence you are constructing. It is not anything related to confidence interval or something, but 90% is reliability factor. So if your national highways or important roads, you choose 90% reliability equation. So this is if it is less significant roads, you choose 80% reliability equation. Okay. So basically this will give similar to our mechanistic ASTO equation as shown. So 90% reliability, you can see the factor is smaller. Okay, which means for the same payment 90% reliability equation give lesser life. Okay, how many times? I think it is about 3 times lesser life compared to the 80% reliability equation. Similarly here as well, this equation gives 3 times lesser life. 90% reliability equation gives 3 times lesser life compared to the. This is 2012 model. There is small modifications to this equation in 2018. I will explain. I will show all those in when IRC 37. So the next thing I want to discuss is so far what we studied is what is the background that is necessary for you to understand IRC 37. Now, if you read the IRC 37, you should be able to understand various aspects of IRC 37. For that matter, any design guidelines, any payment, flexible payment, what we discussed the background. So what I will do now is what exactly is written in IRC 37. That many aspects we discussed already, but from now onwards, I'll be discussing only the things that are written in IRC 37 2018. Okay. Maybe somewhere I will maybe referring to the older versions of IRC 37 as well, but primarily the focus will be on 2018 version. So before I go, if you have any questions, I can take a couple of questions. So have you installed IIT Pave software into your computer?
Yes.
So depending on how far we are ahead, I want to use IIT Pave software as well. So I hope everyone has installed that one. I'll give you, we can discuss one example using IRC 37. Hopefully we will have time, but if not, we will definitely use that tomorrow. But I'm thinking that we can use that today. So
One more, sir. You told that you will see that traffic loading also calculation.
I will discuss that tomorrow. Okay.
Okay.
I haven't prepared that Excel sheet. I'll prepare an Excel. I have some examples with me, but they are very complex. Okay. I want to make a slightly easier version so that everyone can follow. Okay.
Okay.
But I'll have a complete from the starting to ending design example. We will do that tomorrow. Okay. Maybe towards the end of this lecture, we can start from axial load survey and growth factors. From growth factors, how we calculate the design traffic. From design traffic, how we design different types of payments. We'll all have a bigger example tomorrow. Okay. So this is the IRC 37. There are some, say, first I'll start with some salient features. So what are the considerations? So you have, based on IRC 37, you can have different combinations considered in the new guidelines. Okay, I will maybe rather than reading these, what I'll do is I will directly show what are those cases. I will come to these slides as well. Anyway, do not worry, but I'll come to these after showing this way. So this is one type of payment. Okay. This is conventional payment. Okay, you have a bituminous layer, you have unbound granular layer, on the top of subgrade you have a subgrade. Okay, this is conventional fully flexible payment. We call it as fully flexible payment. Okay, so how do we design this one? Okay, so as I was saying, at the bottom of the bound layer, so this is bituminous layer, which we call it as a bound layer, bituminous layer. You want to determine the tensile strain at the bottom of the bituminous layer. Okay, you want to find out the tensile strain, but at what locations? Immediately, this is a one point I want to highlight here is when you are analyzing, analyzing means modeling the pavement section in IIT PAV, you consider a dual wheel. Okay, dual wheels means two wheels, wheel 1 and wheel 2, with each of 20 kilonewton. Okay, 20,000 Newton, 20 kilonewton load. Okay, each carries 20 kilonewton load. Okay, you load it and you model different bituminous layer. Other important point I want to highlight here is whether you have two different layers or three different bituminous layers. Sometimes you may want to put say BC and DBM and BC, DBM1 and DBM2. Okay, still you have to model always in according to IRC 37, you have to always model the bituminous layer as a single layer. Okay, single layer, and you determine the tensile stress at this location, which is the mid. This is, we call it as a zero location. This is zero in y direction or x direction, xy direction. This is 0. Okay, this coordinate is I will say 0 comma z. Say if this is 100 mm, this z will be 100. Okay, at 0 comma 100 you want to find out the tensile strain, and this one is 155. So basically 155 is from this location to up to here. So the distance from here to here is 155 mm. Okay, so at this location, which is 155 mm and 100 mm, that you want to find out at these two locations tensile strain. Okay, so what you do is after finding out the tensile strain at these two locations, whatever the tensile strain value is maximum tensile strain, that you input into our fatigue performance model and find out what is the life and whether that life is within the design life, less than design life, or more than design life, you will evaluate. Okay, that is for design against fatigue. But if you want to, we have another model, rating model. For that rating model as well, say for example, if it is 250 at 0, 250 plus 100. So because Z is the entire depth, isn't it? 250 plus 100, which is 350 mm, and 155 comma at 350. Two locations, at these two locations we'll find out epsilon V, and we again the same maximum compressive stress value compressive strain value we input into our retting model, and we get NR value. Okay, this is how we this is one how we design a conventional flexible pavement, okay, which is having a bituminous layer and granular vertical what we say granular layer and subgrade. Do you have any questions on this one? Because if you understand this point, this thing, I think you understood the entire pavement design according to IRC 37 mostly. Okay, there are some clauses and everything, but if it is not clear, let me know. Okay, and there are some other terminology which I want to focus so that whatever the slides. So we talked about tensile strain near surface. So we do not use, if you see, we do not put any point on here because we do not find out this from the analysis. Okay, but what happens because of these tensile strains, if you look into yesterday's discussion, at the edge of the tiles we get lot of tensile strain. Those tensile strains, what they cause is top down cracking. Okay, but in the design we do not consider as a this in terms of the design, but in design what we are considering fatigue cracking, which is bottom up cracking we are considering. Because of high tensile strain a crack initiates here. For that not to occur, we are designing, okay. And also compressive strain, which is rut depth within the subgrade we are considering. Okay, we are not considering within the structural design, within the analysis, rut depth within the asphalt layer or the top down cracking, okay, or rut depth within the granular layer. Those aspects we are not considering because we do not have models for those distress types. We are just considering this. But what we do is the IRC 37 gives the guidance on how to address top down cracking by selecting mixed properties. We have a rut resistance layers. For example, IRC 37 suggests to use SMA, which is a rut resistant mix when your traffic is beyond certain limit. Okay, and also it also advises the fatigue resistance layer as a bottom layer of the base layer. Okay, if you are having two layers, binder core should be fatigue resistance layer. Okay, so although not as a part of structural design, IRC 37 still considers the top down cracking in terms of and also rutting within the asphalt layer and rutting within the granular layer. But only two distresses that are considered as a part of structural design as bottom up cracking, which is as a part of fatigue resistance at the bottom of the tensile strain, asphalt layer, and the compressive strain, which is the rutting in the subgrade. Okay, because if there are high compressive strains here, there will be permanent deformation within the subgrade. If there is more tensile strain at the bottom of the asphalt layer, there will be cracks initiate and propagate to the top. There will be bottom up cracking. Okay, and the second combination that we have is cement treated. So you have a bituminous layer. Below that, I'll come to what is granular crack relief layer. We have a cement treated base. CTB is cement treated base, and CTSB is cement treated sub base. And you have subgrade, etc. Okay, this is subgrade. So how we design this one? Whatever principles we have discussed earlier, that remains same. For example, at the bottom of the bituminous layer at these two locations we determine the tensile strain, and at the top of the subgrade at these two locations we determine the compressive strain. In addition to that, we also determine the tensile stress and tensile strain. Remember, both stress and strain at the bottom of the cement treated base, because as I said, bound materials crack, isn't it? So cement treated base is a bound material. Okay, so you do not want this to be cracked. So you want to determine the tensile strain and tensile stress, because there are two equations, performance equations, one as a function of tensile stress, other as a function of tensile strain for cement treated base. Okay, so that which I will show later, but this is how we design a pavement with cement treated base and cement treated subbase. And there is one important concept which we have is a granular crack relief layer. Okay, what exactly this one is? If you have a cement treated material, whether it is a cement treated base or anything, you will have a shrinkage cracks, because concrete materials, they crack, isn't it? Cementitious materials, they crack. So for those cracks, shrinkage cracks usually occur at the top of the cement treated base, something like this. So for those cracks, do not propagate through the bituminous layer. What we do is we put a granular crack relief layer, okay, which is a WMA, wet mix macadam. Okay, we usually put a wet mix macadam between bituminous layer and cement treated base, so that these cracks, shrinkage cracks that are developed within the CTB doesn't propagate through bituminous layer and cause cracks in the bituminous layer. Say if there are shrinkage cracks, what happens whenever load is applied? If you do not have a crack relief layer, what happens? There will be more tensile strains at the bottom of the bituminous layer, and those cracks will propagate through the bituminous layer and pavement will fail. To limit that one, what we do is we put granular crack relief layer. Okay, this is how we design a pavement with cement treated base and cement treated subbase. So in addition to conventional, whatever the analysis we have to do for conventional pavement, we have to perform two additional analysis. One is compressive stress, compressive tensile stress and tensile strain. There are two additional models. Those models I will show you a bit later. Okay, and there is a third one. It is exactly the same, but instead of granular crack relief layer, we have a SAMI layer. Okay, SAMI layer is stress absorbing material, intermediate layer. Basically, this is basically what SAMI layer is. Stress absorbing membrane. Okay, so it is a bitumen, high usually polymer modified bitumen. Maybe if you are comfortable, it is PMB, and smaller size of size aggregates. Okay, so we put as a thin layer of SAMI layer in between bituminous layer and CTB. The function of SAMI layer is same as crack relief layer, but instead of having an unbound materials, we have a thin layer of SAMI material with PMB and small aggregate size. What it does is it is very flexible layer. Okay, so having flexible layer, what it does is it can take more strains, and whatever the shrinkage cracks that are developed here, they will not propagate through SAMI layer and reach the bituminous layer. Okay, but the design is same, exactly the same. You will have to do analysis for the strains at the bottom of the bituminous layer, bituminous bound layer, at the bottom of the cement treated base, and at the top of the subgrade. Okay, vertical subgrade strain, tensile strain at the bottom of the bituminous layer, and tensile strain and tensile stress at the bottom of cement treated base. Okay, this is exactly the same.
Sir, CTB is the same as the soil stabilization treated with cement?
Sorry, say that again. No. Cement treated base is different. So cement treated base has got, actually it is more of unbound materials. Okay. Like granular base or granular subbase, similar to those gradation, but you add cement.
Okay, sir.
Not exact gradation, but similar gradation.
Okay, sir.
Stabilized soil is different.
Okay, sir.
Okay, this is another combination of pavement that is given in IRC 37. This is using the recycled material. Okay. So recycled material with either you add emulsion or foam bitumen treated mixes. What you do is if you are having emulsion treated or foam bitumen treated bases, stabilized bases, it is same as conventional pavement. You have to run the analysis at the bottom of the bituminous layer and at the top of the subgrade. Okay, but instead you have an stabilized base here. Say if you are doing recycling, okay, or if you have a stabilized base, you have to consider design as such. So this is what we call another one, which is cemented base, granular subbase. Okay, you have a cemented base here, granular subbase. It is same as the one which we discussed earlier with the CTB and CTSB. We have discussed the case, but we do not run the fatigue analysis for CTSB. We run for only CTB because CTSB is having less cement than the CTB. So this usually do not fail in fatigue because it adds more as a strong granular material rather than a bound material. Okay. Finally, this is the final case in which you have CTSB granular base. As I said, you do not run the analysis for the fatigue analysis for CTSB. Granular base on the top of that granular base bituminous layer. It is same as the conventional pavements. Okay. You have any questions in analysis? Okay. The location points of the important point from all these combinations is for different combinations of material where you have to perform so choosing these points. Okay, these points is the important thing that I want to discuss. Okay, I wanted to discuss these things. So you have to
sir, can you shed more light, sir? Can you shed more light on CTSB, the composition of the particles of CTSB and CTB?
No. So they are actually CTB and CTSB are similar to granular base and granular subbase, but with cement. Okay, this CTB will have more cement. CTSB has less cement, but I will. So CTB, maybe I might have a slide here. I will show you the requirements for CTB and CTSB. So CTSB,
sir, sir, if we have the issue, sir. Sir, if we have the issue like the wildlife, they don't allow the bituminous layer, BM layer. So we have to stop at the base layer. And for that road we have a lot of traffic. So can you guide us how we will design that? Because they don't allow the wearing course, the BM course. So we have to stop at the base layer, and the traffic is large. For that road, yes.
So base layer is it bituminous base?
No, sir. We have to stop at base is not bituminous. It is granular.
Granular base. And for how many days you open this one to the traffic?
Sir, after 4 or 5 days.
So there is actually, I will discuss in this one. In IRC 37 there is a clause called staged construction. Okay.
Yes, sir.
Staged construction, which I will discuss in this presentation only. Maybe if possible today. Otherwise, definitely I'll be touching. I have a slide as well on staged construction. I think. Yes, staged construction. Okay, which I will touch on this point what you are discussing. Also, there is another clause in which we there is an approach in which we consider, for example, whether the design is safe for construction traffic and also the traffic you are talking about. If you are leaving for 4 days, whether the design is safe or not to leave that amount of traffic. If it is not safe, how to address that one? There is a clause which we'll discuss as well. Okay, as a part of this my lecture, I have that discussion as well. With example, we'll discuss. Okay.
Okay, sir.
But let me finish the main conventional designs and all these things, and these non-unconventional ones, like whatever one is staged construction, and the second is whether the unbound material thickness is sufficient for to carry out the to take the construction traffic, and also the additional unexpected traffic that we'll discuss. Okay.
Does the mastic asphalt layer of 25 mm affect the tensile strain at the bottom of bound layer?
Sorry, say that again.
Sir, a 25 mm thickness of mastic asphalt layer on the surface, does it affect on the tensile strain bottom at the bound layer?
Okay, so that question is whether you want to consider mastic asphalt as a structural layer or not. I think yes. According to me, it is yes, but some people say otherwise. But according to IRC 37 as well, you can consider. Okay, mastic, if you are putting.
There is effect on the tensile strain and at the bottom of the bituminous layer?
Yes, yes, because that, as I said, you can consider that as a structural layer.
Okay, sir.
Okay, if you are considering, so that means like this thickness, whatever thickness you are having here, you are increasing. Say for example, you have a bituminous layer of 100. Okay, on the top of that you are putting 25 mm of mastic asphalt. So your thickness will be 125 mm of bituminous layer. Okay. So if this H1 is this is H1 is increasing, your tensile strength will decrease. Okay.
Okay, so it means that it is the same effect that the other bituminous layer like BC and DBM.
So in theory not, but according to IRC 37, that's how we have to analyze. But we can assume it will have the same effect. Okay.
Okay, sir. Yes, sir. Thank you.
I discussed what are various combinations, how we handle these different pavement composition, pavement design. So now I'll go to these first few slides, which may be more clarity. So these all 6 are various combinations we have discussed. And so major distresses that IRC 37 address is through structural design, bottom-up cracking, okay, in bituminous layers, okay, cracking of cemented bases, and subgrade rating. These 3 through pavement analysis and performance models. But top-down cracking rating in bituminous mixes, in terms of we integrated these within the design through mixed design. Okay, not directly, but indirectly we address these stresses. So the importance of following has been recognized. So retting resistance bituminous surface layer, for example, IRC 37 talks about the use of SMA, gap graded rubberized mixes, GGRB, which are ret resistant mix. It recognizes those and recommends bottom bituminous layer with better fatigue performance. Okay, so if you remember, I was talking about here fatigue resistance layer. So if you are having 2 layers, so top layer and bottom layer, you have a fatigue resistance layer. Usually what the fatigue resistance layer is, conventionally, if the bitumen content, obviously this is up to a level, so more the bitumen content, usually the better the fatigue life of a pavement. It has a good fatigue resistance. That is the principle of SAMI layer as well. So obviously it should not be so high, it ret resistance should not come down, but it can be more than the conventional mix, so that it will have better fatigue resistance. Okay, so if you incorporate more bitumen into the somehow without compromising on other properties, usually it will have good fatigue resistance. Okay, that we consider within the design indirectly, rather directly I should say. And also there is recommendations that are given in the top-down cracking resistance of the surface layer. And also the importance of consideration of effective subgrade CBR is considered. I will discuss what is effective CBR in coming slides. and use of stabilized, okay, both cement stabilized, emulsion stabilized, foam bitumen stabilized aggregates. So you can there is a design approach for these mixes is also given, and stabilized cement stabilized bases and sub base also you can incorporate. So there is lot of flexibility. Sorry, I think this is 18. Okay, there is lot of flexibility within for use of stabilized aggregates, stabilized wrap. I think most of you know what is wrap material, reclaimed asphalt pavement material. Okay, once pavement is failed, you recover that, you mill that failed pavement, and you can use that material for producing emulsion stabilized mixes and cement stabilized and foam bitumen stabilized mixes. Okay, so stabilization of bases, sub bases, and subgrades. So you can incorporate all these combinations can be considered according to, again this is 18. Okay, load associated failures is considered as a mode of failure in the design of flexible. We have discussed that. Environmental effects are built into the retting and fatigue equation. So when the fatigue and retting models are calibrated, these environmental effects were automatically considered. Okay, you can mix and match different combinations. You can be using any layers we discussed, any materials we have discussed so far. Okay.
One more question.
Yes,
The
please.
bituminous layer will come in the rut resistance layer or fatigue one?
Sorry, say that again.
Bituminous concrete layer.
Mm-hmm.
It will come into the rut resistant layer or fatigue resistance?
So it is the bituminous concrete is a rut resistance layer. See, usually I'll tell you what exactly it is. Okay, maybe I'll use this one. So typical mix types, I'm just writing here. So if you are having only one layer, if you are putting, okay, I'm talking about an highway, you put bituminous concrete, SMA, and gap graded rubberized bituminous mix. Okay, these two are rut resistant mix. Okay, this one is also rut resistance, but you have to use in all three of them. If you are use a polymer modified bitumen, you can consider this as a rut resistant mix, but we traditionally call these two as a rut resistant mixes. Okay, and here this is in this layer. In binder course or bituminous base, we use a DBM, dense bituminous macadam. Okay, which we consider if we design this to 3% air voids, okay, by incorporating more bitumen, then we call it as a fatigue resistance bitumen. So BC is not, we do not call it as a rut resistant mix, but it has good rut resistant properties if you put polymer modified bitumen or VG40, which is a harder grade bitumen. Okay, but traditionally we call these two as a rut resistant mixes, SMA and gap graded mixes. So the performance criteria we discussed, subgrade rating criteria, this thing. So I'm not discussing again this part. So NR is subgrade red life cumulative equivalent number of 80 kilonewton axis. So you run the analysis for a trial payment and you get the epsilon V at the top of the subgrade. So vertical compressive strain at the top of the subgrade calculated using linear elastic theory, which is the IIT PAVE runs on a linear elastic theory, by applying a standard axial load at the surface of the selected pavement. This is what we have discussed in vertical compressive strain, which is epsilon V at the top of the subgrade. If you see vertical compressive strain, this is vertical compressive strain at the top of the subgrade. This is subgrade at the top of the subgrade. When you run the analysis in linear elastic layer theory, which is the software which does one, and place a standard wheel. So standard, what is standard wheel? Dual wheel with the, say, remember, although our standard load is a standard axial, but analysis we run for a standard wheel, which is, say, for example, This is our standard wheel, isn't it? Standard axle. Standard axle with 80 kilonewton. But analysis we do not run for standard axle. We only take this part, okay, and simulate or model that in the model, as you can see. So only this part means this is 40 kilonewton together. Okay, but if we for each wheel it is 20 kilonewton. Okay, so only we model this part. When a standard wheel is placed on the top of the surface of the pavement, so that is what this one, everything. So top of the subgrade calculated using linear elastic theory by applying a standard axle load, or in terms of we should call wheel load as well, at the surface of the selected pavement. Okay. So coming to the fatigue criteria, if you look into the fatigue criteria, I already discussed this part. Only part that was not discussed is this term C. Okay. Earlier we discussed about what is this one. MR is resilient modulus. Epsilon T, we know what is epsilon T. So someone has some question. I don't know who this. Someone has put
It's a Salma. Mic is unmute.
Yes, sir.
Please mute your mic.
Okay.
Doctor, you can go. Hi.
Okay, thank you. Okay, so we discussed this. So only parameter that we didn't discuss is C. Okay, so we talked about bottom rich bitumen rich pavements or a fatigue resistant pavements, isn't it? The bottom layer. So we are incorporating into the structural design by this factor C. Okay, C is 10 power m. M is 4.48 multiplied by VBE, which is effective bitumen volume, and VA, air voids. So what we want is, as I was saying, for a fatigue resistance mix, you want more bitumen and less air voids. Okay, so if you have more bitumen and less air voids, your M value will be high. If your M value is high, your C value will be high. If your C value is high, your number of cycles to failure will be F. So this is a kind of indirectly incorporating the fatigue bitumen rich fatigue layer into the pavement design. Okay, so as I said, VA is the percentage air voids in the mix used in the bottom bituminous layer. VBE is the percentage of effective bitumen mix used in the bottom bituminous layer. NF is the fatigue life, 80 kilonewton axle, 20%. We discussed this about 20% or more cracking. Okay. Epsilon T also we discussed maximum horizontal tensile at the bottom of the bituminous layer, TBM. So obviously MR is resilient modulus. So these two we already discussed, and now I discussed what is C and what is the importance of C, why we introduced the IRC 2018 in the C was introduced. Okay. But there is two performance models which we have not discussed. That is for the cement treated base. You can see this is the performance model for cement treated base, which is N, again the same definition of N is the same number of standard axle loads for repetitions for CTB can sustain. Okay, so beyond these number of loads for that particular pavement, particular thickness of CTB, it cannot sustain. So you have epsilon T, which is the tensile strain at the bottom of CTB layer. I will come to this point. Analysis done at 0.8 megapascal. And we also have another term called reliability factor. Reliability factor for cementation material. You use a value of 1 for expressways, national highways and state highways, and 2 for all other cases. Reliability factor is the same as our 80% 90% reliability, but it actually you can see For expressways, we are taking high reliability, means this factor is low, which means this N value will be lower. If you are using for the same pavement thickness, this N value will be lower if your reliability factor is low, which is we are using for expressways, national highways and state highways and urban ways. If it is low volume roads, we use this as a 2. Okay. Now coming to the analysis to be done with 80 megapascal, this is very important. So we, for example, will go for our conventional case. Okay, in this conventional case,
Sir, what is effective percentage bitumen?
so VBE, which is effective bitumen volume. Okay, so for example, you are designing a bituminous concrete mix. You produce the mix with 4.5% of bitumen or 5% of bitumen. But not all bitumen is participating in coating and everything. Some of the bitumen is absorbed by the aggregate, isn't it? So, for example, you are using aggregate with 1% water absorption, okay, which is allowed as per IRC 37 and other IRC guidelines or more guidelines. So it has a potential to absorb up to 0.5% of bitumen. So whatever remaining bitumen, in terms of volume, we call it as a effective bitumen volume. Okay. So some of the bitumen that is not absorbed, the bitumen that is not absorbed by the aggregate, that is an effective bitumen volume. So coming to what I'm trying to discuss is, so when you are designing a pavement, so we give 20 kilonewton load on each beam, and we give a stress, effective stress of 0.56 megapascals. Okay. We continuously said in the linear analysis, we use a circular contact area and uniformly distributed load, isn't it? Uniform stress distribution. So that uniform stress is 0.56 megapascal. That what we use for analyzing the life or the cycle number of cycles to failure at the bottom of the bituminous layer and for the top of the subgrade. For subgrade rating criteria and bound layer fatigue criteria, we use 0.5 megapascal uniform stress. Whereas for the CTB, if you are analyzing for the CTB, instead of 0.56, we should use 0.8 megapascal. Okay. We should not use 0.56 if you are running the analysis for CTB, cement treated base. So this is one important thing you have to remember when you are designing the pavement. Okay, this is for the tensile strength. If you remember when I'm talking about CTB, we also have to determine the tensile stress as well, isn't it? That tensile stress, we have this equation. So we have this expression, which is what we call it as a cumulative damage approach. So what we here we have is a where is that one? Okay, so NFI equal to, you have a tensile as a function of tensile stress modulus of rupture, which is 28 days flexural strength of the cementitious base. So basically this is what we call it as a stress ratio. You will determine the stress ratio. Whatever the stress you are getting within the stress ratio, and you input this one and we calculate the NFI. NFI is fatigue life of the CTB material, which is the maximum repetition of axial load class I of the CTB material can sustain. So this is very important and the most complex aspect in I mean one of the most complex aspect in IRC 37. Okay, maybe so in other three analysis, whether the strain analysis. So tensile strain at the bottom of the bituminous layer, or tensile strain at the bottom of the CTB layer, or the compressive strain at the top of the subgrade. We are performing it to the, we are comparing these with the number of standard axes. Okay, whereas for the cement treated base, it is different. Okay, it is what we do is, rather than doing this one, we run the analysis for each axial load class. Okay, you have seen earlier different axial load classes, isn't it? So 20 to 31 axial load class, kilonewton, 30 to 40 1 kilonewton, one axial load class, and for different axial types, single axial, tandem axial, tridem axial. We we have seen different axial. For each axial class, we have to run the analysis and find out the design life for this one, and we call it as a cumulative damage approach. So what I'll do is, I will discuss an example tomorrow with the cumulative damage approach, so that it will be more clear. Rather than spending more time here, I'll spend on other aspects. But remember, you have to run the analysis as 0.8, and you have to run for each axial load group and find out the design consumed by each axial load group. Sum of all the damages, if you remember the minus principles, should be less than 100%. That is what we try to find out. Okay, but what exactly it is it will be more clear if we do one example. Okay, so after example, during example, if you have any more questions, we can discuss at that time. But the concept is, you want to find out damage caused by each axial group individually, and sum up all the damage, and sum of all the damage has to be less than 100%. Okay, so this point as well, like for example, one tandem axle, if we have a tandem axle, we consider as a 2 axles and run for 1 axle and take 50% of that load. And if it is a tridem, we consider a single axle with 1/3 of the traffic. Okay, I will discuss with an example tomorrow. So this is summarizing what we have discussed so far in terms of IRC 37. Material response model, we said linear elastic model we use. Okay, layer interfaces, fully bound. All layer interfaces we consider as a fully bound. Like, that is, fully bound means full friction is developed at the interface of 2 layers. Okay, the analysis we run is a dual wheel. As we discussed, we modeled as the two wheels, with each wheel carrying 20 kilonewton wheel load, and a contact stress we use is 0.5 bituminous layer, tensile strain bituminous layer, and vertical compressive strain of the subgrade, and 0.85 for cement treated basis. Okay. And the critical mechanistic parameters is, I think someone again has turned on the. So the critical mechanistic parameters we are considering are, as we discussed, for the bituminous layer, it is tensile strain at the bottom of the bituminous layer. For cement treated base, it is tensile strain as well as tensile stress. For subgrade, it is tensile, compressive strain, vertical compressive strain at the top of this subgrade. So you can see only absolute. This I will discuss when we are talking about the software itself. So when you run the analysis, only absolute values of the stresses are strain. So when in the IIT PAVE, there is sign convention, which I'll discuss tomorrow. But we forget about sign convention. We have to use whether it is a positive or negative. So basically, we use tension positive and compression negative. So if you are For compression tensile strain, you get something like that 0.003, something like that. For compression, you get minus. So although you get in minus, you have to take absolute value. Okay.
Sir,
Yes.
sir, wheel load 20 kilonewton. It is a fixed criteria, or it will be changed?
Yes, it is 20 kilonewton is fixed because we are converting everything into standard axle, isn't it? Standard axle is 80 kilonewton. So 80, what is our standard axle? Dual wheel, single axle, isn't it? Which is 80 kilonewton. So 80 kilonewton standard axle means on each wheel it is 20 kilonewton load, isn't it? So that is fixed. So coming to the design periods that are recommended in IRC 37 is 20 years for national highways, state highways and urban, and 15 years for other roads. And there is an approach called long life pavement, which you can design up to 30. Say for example, in some locations you get a traffic up to 300 million standard axis. Okay, maybe in that case it is worth considering long life pavement. What is long life payments? We'll discuss through examples tomorrow. Okay, in 2012 version, these values are different, and I was talking about reliability. Okay, 90% reliability is for expressways, national highways, and state highways. We have to choose the 90% reliability equations. Okay, or we also talked about reliability factors. Okay, reliability factor of 1 for expressways and national highways, and 80% reliability equations, or a reliability factor of 2 if we are talking about CTB equation for other roads. Okay. So this we discussed. Okay, the traffic, how we convert how we derive the vehicle damage factors also. As I was saying, there are default values that are given in the IRC 37 as well, but you can get the axle load damaging factors. From the axle load damaging factors, you can use the vehicle damage factors as well. Okay, this thing we have discussed already. Okay, this part as well we discussed, but we will discuss with an example tomorrow, so it will be more clear. So if your end design is cumulative number of standard axes, okay, if it is a small project, you can directly use the D value that are default values that are given in IRC, and you can incorporate this one, which is A is initial traffic and F is vehicle vehicle damage factor, D is lane distribution factors. So I was talking about D, not D. F is vehicle damage factors. Apologies. Okay, but if it is a project is a bigger project, maybe we have to do this one for each vehicle group. Okay, we discussed about different vehicles: 2 axles, 3 axles, LCVs, low commercial vehicles, buses. For each category of that one, we have to apply this formula and sum up all those vehicles to get the design life in terms of standard axis. Okay, we also talked about lane distribution factors. Here, this is the D is for the lane distribution factors. Okay, I'm not discussing because exactly these values we discussed. That's why I'm not considering. So now coming to the material properties, how we can consider the material properties, and also I will talk about what is effective CBR as well. This one. Just so coming to the subgrade, so minimum effective CBR criteria is given, has to be 5%. Okay, if you have two-way commercial vehicles per day is more than 450. Okay, then you have to have an effective CBR of 5%. For example, if you are having a embankment or the existing soil of say 3% CBR. I'm not discussing what is CBR, assuming you know what is CBR. But you have to have at least 5% CBR. So what we do is we borrow the material from other places and we use say 8% or 10% CBR material. Obviously this is 500 mm and compact, and maybe we might achieve more than 5%. But how do we know we are achieving more than 5% or not? How do we evaluate? Okay, so whatever CB, that is what we call it as a effective CBR. So effective CBR of these two layers has to be more than 5%. How do we evaluate? There is a procedure that is given in IRC 2008. Say for example, this is the chart that is given in 2012, but this will I'm using this one to explain what exactly is the effective CBR. But the concept is still retained in 2018 as well, but this chart is removed from 2017. Say in the previous case, okay, my CBR is existing CBR of the existing soil is something around 3%. Okay, 3% CBR. Now I cannot construct a pavement on the top of this because I want at least 5% CBR if the commercial vehicles per day is more than 50. So I brought a borrow soil, okay, and I constructed 500 mm of subgrade on the top of this, compacted to 97%. I brought 10% CBR material. Now I want to check whether the effective CBR, the CBR together of these two layers is greater than 5% or not. What I can do is, so the CBR of compacted borrow material is whatever I brought is 5%, and actually this is line, isn't it? So this is the line for the 3%. So this is 3% CBR. I'm looking for a CBR below 500 mm. This is the one for this line. Okay, and my borrow material CBR is 10, and what I do is I find out this one, and you can see the CBR is around 6% or 6 or 6.5. Okay, so and okay, this is now greater than 5%. You can construct your payment, and also it is 6% CBR. Okay, what you found is this 6% CBR. So when you are designing a pavement, you have to model your pavement as in your model pavement with only single layer of subgrade. Say for example, as I was saying in the beginning, you model your pavement as a single layer of bituminous layer and single layer of subgrade. Okay, for example, if you have constructed this one with 3%, top 5%, and this one as subgrade, you cannot design it as a 2 layers. Okay, I have 500, I'll model it as 500, and below it the CBR as 3%. Okay, no, we should not be doing that. We should be considering entire these two layers as one layer, which is here. Okay, so now I got 6% CBR. When I am modeling in the IIT PAVE, I consider this as a CBR subgrade with 6%. Okay, so you may get different cases. Okay, in different scenarios you may have to do that. Say for example, what are those cases, I'll discuss a bit later, but I hope you understood. So but how do we analyze without the charts? I will also discuss that point a bit later. So obviously, although I'm talking in terms of CBR, CBR is not the input that we need for the analysis. We need resilient modulus. So IRC 37 has given two equations how we can convert CBR into resilient modulus. If your CBR is less than 5%, you multiply the CBR with 10, you get, say for example, the 3% CBR, you want to input that into a IIT paved. So what you do is 30 megapascal, 3 into 10, 30 megapascal as a resilient modulus that you input into the software. But if it is CBR is more than 5%, this is the expression you have to use, 17.6 multiplied by CBR multiplied by 0.64. Okay. So this is what I was trying to say. So sometimes there can be a significant difference between the CBR value of the soils used in the subgrade and in the embankment layer below the subgrade. Okay, say for example you have an embankment with CBR of say 8%, and you borrowed some material and constructed a subgrade on the top of this one with CBR of 20%. So as I was saying, we cannot model, we should not be modeling. It is not that we cannot, we can obviously, but you should not be as per IRC 37-2000. You have to model these two as a single layer. So that what we do is we have to determine the effective CBR or effective modulus of these two layers, effective resilient modulus of these two layers. Okay, how do we determine that effective modulus of these two layers is, first what we do is we model this as two layers. As you can see, I think 66.6 is, I do not remember the, just give me a second. What would be the CBR values? I think it is the same. Whatever I have given here is, so if you input this 8% into the equation I have given earlier, yeah, so if you input this value CBR 8%, 17.6 multiplied by 8 power 0.64, then whatever value we get here is 66. Okay, similarly you brought the borrowed material from somewhere, which is 20%, so 17.6 multiplied by 20 power 0.64 is 19.7 megapascal. Okay, so you model this pavement, and what we do is we put a single wheel load with 40 kilonewton. So remember, except in this case, everywhere we use 20 kilonewton, but here only for this case we use 40 kilonewton and a contact pressure of 0.56. 40 kilonewton, but a single wheel. We will not give the dual wheel. We give a single wheel of a 0.5 kilopascal and run the analysis, and we determine the deflection, whatever the deflection we are getting here. Okay, so we use this deflection value, and there is an expression given in IRC 37. I think I haven't copied that one here, but let me share. So can you see here? Can you see the equation on the screen?
Yeah, it is visible.
Okay. So we have got we found out deflection value. Okay, from the analysis we have a p value which is a contact pressure of 0.5 and a radius of contact area. If you calculate the contact area radius, you get 150 mm, and you Poisson ratio of 0.35, then you can calculate the MR value from this equation. Okay. So, for example, using this equation, if I get I'll get some value. Say, for example, I think I will get MR of 105. Okay, for 105 MR, what would be the CBR? You again 105 equal to 17.6 multiplied by CBR power 0.64. Okay, so then you can determine the CBR and you will get the effective CBR. Okay, this is how we calculate the effective CBR if we are using two different materials. And other point maybe you may have to remember is, okay, although you get 105 as effective modulus here, okay, but in the analysis we should be using a maximum value of 100. Okay, you should not be using more than 100 megapascal for subgrade modulus. Okay, remember these points. Okay, so maybe with this one I will close here. So I want you to do, I can take a few questions before I leave, but I want to discuss one or two things. Okay, so first thing we do tomorrow is we'll exactly whatever we discussed so far here, we will do this in IIT PAVE. The first thing we do tomorrow is we solve this one, the problem that we discussed in IIT PAVE using IIT PAVE. Okay, that will be the first thing. Obviously, I will be discussing other examples and as I said, staged construction, how we can address, and if we have a cement treated base, how we do cumulative damage approach, how all these cases we'll discuss one by one, but we'll start with this effective CBR calculation. So when you are coming tomorrow, make sure that everyone install this IIT PAVE software. Okay, and maybe the installation guidelines are in IRC 37. You can go through and install. It is very easy. You can install in 2 minutes. Okay, and maybe if possible, although I will demonstrate, just familiarize with yourself. But the important thing, okay, other important thing other than installing is just go through IRC 37 briefly, or I will share these slides with you, or at least go through the slides and try to understand what we have discussed, so that when we are discussing the example, it is easy to follow for you. Okay, so these two are my advice for you, so that it will whatever we are discussing tomorrow, it is easy to follow. Okay, although I have quite a few to discuss, but many of them we already discussed, or some of them are very obvious things. Okay, but many of them are the examples that we will be discussing anyway tomorrow. Okay, so I can take few questions before we leave.
Hello.
Hello, yes.
Hello.
Yes, I can hear you.
G. My question is regarding the subgrade. So, and below 500, we have to calculate the effective CBR.
Yes, that's true.
See,
So if you are
you
having
told that suppose if my 500 subgrade is like 20 CBR, and below that my CBR is 2%. I have to enter this both in the ITPO, right?
So you have to convert that into elastic resilient modulus and enter into IITPO. So 2% CBR is according to these expressions, 10% of 10 times of CBR. Your 20% is 17.6 multiplied by CBR power 0.64. Any other questions?
Sir, what is the criteria for reducing CBR value in IRC 2018? It was 8% in 2012. What's the criteria for selecting those CBR values?
No, earlier it was thought that 8% CBR, unless you have an 8% CBR, the red resistance, I mean, there will be, if you are having lower CBR, there will be more, what we say, deformation in subgrade. But now because we are putting some more material and people, actually many of them are, this is not based on any performance data or anything, but it is more of a feedback that has come from the industry. Okay.
Okay.
So any other questions? So my if you do not have any questions, you can leave. But my advice is to definitely, obviously, you install the software. Tomorrow, most of the
Sir,
part.
there are some questions in chat box.
Oh, there are some questions in chat box. Let me see the chat box. Let me see. Oh, there are quite a few. So how to convert tandem and tridem axle to a standard axle? So how to convert tandem standard axle? We have given here na, this expression. So we use if you are using a tandem axle wheel load one, you use axle load in kilonewton, whatever the axle load group. If it is 80 kilonewton axle load group, you divide it by 148, so that you get a factor, axle load factor, and you multiply with that frequency, so that it will be converted into standard axle load. Similarly, tridem, this is the equation. Okay. I hope that is clear. Mr. Sai has asked this question, but if it is not clear, you can ask. So according to VDF concept, we will get VDF for each vehicle type. That is right. HCV, LCV, right? Yes, that is right. So as I was saying, if it is a big project, you have to calculate the VDF of the vehicles individually and use that 365 multiply whatever the expression that has got. You use that expression and sum up all individual standard axes for each vehicle category. And so what is the significance of considering 80 or 90% reliability? So as I said, like for the more significant roads, we consider 90% reliability. 90% reliability is, that is basically you can think of in terms of confidence. Okay, 90% performance equations, they give less number of road repetitions. So basically for the same pavement, if adopting 90% and 80%, 90% will give approximately this is rather than giving different equations for low volume roads and high volume roads, we have provided the same equation. Less important, you can think of less important roads and more important roads. Okay, we have given the same equation, but as a reliability, the factor will change, so that less important roads will get lesser thickness for the same traffic. Okay, why we are considering 0.m mega? And also, if you want to understand this reliability concept, you may have to understand how the performance equations has come, which I haven't discussed because considering the time, but I hope you understand. So this is why we are considering 0.8 megapascal for cement treated base. This is a good question actually. So this is Mr. Chakravarti, Saralya Chakravarti has asked why we are considering 0.0 megapascal for cement treated base instead of 0.6 megapascal for all the other analysis. So 0.56 we are using for retting and retting on the top of the subgrade and the fatigue at the bottom of the base layer. Okay, those equations we have developed based on, as I was talking yesterday, based on the, is Mr. Chakravarti is there still?
Yes,
hello?
sir, I am here. I am here, sir.
Okay, so basically those two equations, they were developed based on the data collected in India. So Those are developed within India, and at the time of developing those equations, we used 0.56 megapascal. They have used 0.56 megapascal stress levels and calibrated the models based on such analysis. But the other two models for CTB we borrowed from Ostro's. Okay, when they are developing those equations, their contact stress area is 0 megapascal. That's why we have to run the analysis for 0.8 megapascal. Otherwise, if you run for the 0.8 megapascal, that is not what they have calibrated for. Okay, that's why we have two different models.
Okay, sir. Thank you, sir.
Okay, I think Mr. Sai's question as well. Mr. Sai, you are still there?
Yes, sir, I understood this. Thank you, sir.
You understood. And I think someone is asking my mobile number. Let me put my mobile number here. Let me stop sharing. Maybe it might be easy. So this is my mobile number. If you have any questions, you can message me. And this is my mobile and WhatsApp number as well. Okay, hope this is clear. But if you have any questions, we can obviously discuss tomorrow as well. Okay, thank you very much.
Okay, thank you.
Okay, I'll obviously I will share these two slides as well. Today I will also send. Maybe you will be getting those.
Down, sir. Okay. Sir. Oh, Manju. Ani kona? One number. Huh? Oh, wait. Okay.
Dr. Kuna? I think the session is over. Can anyone respond?
Okay, thank you, sir.
Okay, thank you, Mr. Sagmar.